By now, I think most of you are convinced that the meromorphic transfer theorem provides a really pretty simple turn-the-crank method for doing the last part of analytic combinatorics, giving us analytic transfer right to asymptotic estimate of coefficients for a big variety of combinatorial classes. Next, I want to introduce an even more important concept, the idea of a schema, where we can have a general theorem that directly gives us results for a whole set of combinatorial classes all at the same time. There's many examples of this in analytic combinatorics. This is the first of many examples that we'll see. The idea is of a schema. So that's a treatment that unifies the analysis of a whole family of classes. So that we do the analysis once and we don't have to do it again. You could think of our transfer theorems as that way, but you'll see the distinction. So for example, what we're going to talk about now is all combinatorial classes that are built using the sequence construction at the top level. So if a class has the form f equals sequence of G, where G is any class at all, labeled or unlabeled, then we're going to say that's a sequence class and it falls within the sequence schema. And then what we'll see is a way to get coefficient asymptotics for sequence schema just in terms of the generating functions for these top level classes. So for example, for enumeration, we know that if f is a sequence of G, then the generating functions satisfy the relationship f of z equals 1 over 1 minus g of z, where these are the coefficients. This is for the unlabeled case. The number of structures we're talking about is f sub n. For the labeled case, it's n factorial f sub n, and we've seen examples of those. But what's also interesting is that we can use the same approach to analyze parameters. So like if you want to count the number of G components in F, so it's a sequence of G's, there's a number of, how many different G's, how many G's are there in F, then you can just mark it with a variable u, as we saw in lecture 3, and get this relationship that the bivariate generating function for F has to satisfy in terms of the generating function for G. Or maybe you want to mark the number of components of size k. So then you take the ones of size k and mark them with u and take them out, and then you get an equation like this for the generating function, the bivariate generating function for number of components of size k, and so forth. The idea that it's a sequence class gives us a relationship among the generating functions, and we can exploit that in the analysis with meromorphic asymptotics. Now what often happens, and this is the first again of many examples, is when we're looking at the generating function as an analytic object, there's some technical condition that we have to assume about the generating function in order to be able to apply the analytic results. So maybe there's something like Pringsheim's theorem that gets rid of that technical condition out there, but for a lot of these we don't know those. But usually, as you'll see, these conditions are easy to check and they hold. So for sequence classes, it's the idea of supercriticality. So what we're going to talk about is supercritical sequence classes, where we mix up the formal and the analytic. And we're going to say that a sequence class is supercritical if you look at the generating function of the G class, the component class, you have its generating function g of z, and it's got a radius of convergence. And the thing is, if you evaluate the function at its radius convergence and it's bigger than 1, then we're going to say that the sequence class is supercritical. And that's the condition that we need in order to be able to unify the analysis. So just as an example, we did the generating function for integers a while ago, z over 1 minus z. So the radius of convergence is 1 minus epsilon for any epsilon. So if we evaluate it at rho, then we get 1 over epsilon minus 1. And there's plenty of values of epsilon within the radius of convergence for which that's bigger than 1. So as long as we pick a small enough epsilon, then we have the supercritical condition satisfied. And so, and then we can do this test for the other combinatorial classes that we looked at. So anyway, since I of z has this property, the class of compositions is supercritical. It's the G that we're testing that has to have this property that if you evaluate it at its radius of convergence, you get bigger than 1. So since integers has that property, compositions is supercritical. Now, in the book, there's a full treatment of what happens when there's periodicities in the generating functions. And we're going to, just for simplicity, because really I just want to get across the idea of what a schema is, we're going to ignore periodicities in this lecture. And so we have another technical definition called strong aperiodicity that says that there's not going to be periodicities in there. So given those two definitions, now we have a general transfer theorem for the whole schema, and it gives an even simpler way to derive the coefficient asymptotics for these types of classes. So it says that if F is strongly aperiodic supercritical sequence, then its coefficient asymptotics is just 1 over G prime of lambda, and the growth is 1 over lambda at the n plus 1, where lambda is the root of G of lambda equals 1 in its radius of convergence. So we find a root, but it's a simpler root, and boom, we have the coefficient asymptotics. And it just is just a quick sketch of the proof, and it's technically not so difficult. First of all, the function increases from 0 to its radius of convergence, positive coefficients, and the value at rho is bigger than 1, so there is a root in there. There is a value where G of lambda equals 1, and that's the one that we're going to look for. And then at that point, you can write out the series expansion of what G would be. And then if you take 1 over 1 minus G, then that's gives you the leading term in that, essentially gives you the coefficient asymptotics. That's just a quick outline of the proof. But really, most people are going to remember from this slide is this idea that all I have to do is find lambda and evaluate G prime at lambda, and I've got the coefficient asymptotics. So just to look at the examples that we already looked at, for example, for surjections, that's a sequence of non-empty sets. So it's 1 minus e to the z minus 1, so that's what G of z is. And so lambda is where G of z equals 1. So that's e z equals 2, lambda equals log 2. So boom, log 2 to the n plus 1. And then G prime is just e of z, evaluated lambda is 2, and that's it. Such an easy way to get from the construction right out to the coefficient asymptotics. Find the root, that's the exponential growth. And again, this is just another example of our basic paradigm in analytic combinatorics, so going from the spec to the generating function equation immediately to the asymptotics. And here's another one that we did was alignments. So now G of z is log of 1 over 1 minus z. Whereas log of 1 minus z equals 1, we already did that calculation. It's 1 over e, boom, 1 over e to the n plus 1. Derivative is 1 over 1 minus z, evaluated 1 over 1 minus z is e, boom, that's it. Compositions, that's the one we've done. G of z is z over 1 minus z. Where's that equal to 1? At 1/2, boom, 2 to the n minus 1. An even easier way to do coefficient asymptotics for a whole class of combinatorial classes, whole family of combinatorial classes, the ones that are built with the sequence construction. That's an example of a schema, and we're going to see other examples later on. Now, you might argue that's not really that much of an improvement. The other method was pretty simple as well, and there's some truth to that kind of argument, but what I'll show you next really maybe gives a feeling for why schema are so powerful. So say you want to study parameters, like how many parts are there in a random composition. It's like for 2, it's one of them's got 3, 2 of them have 2, and one of them have 1. The average is 2. And actually, well, you can probably figure out what you think the number of parts is in a composition. But of course, the same method's going to work if we restrict to 1s and 2s or primes or whatever else. Let's look at surjections. If you have a random surjection, what's the expected value of m? That's a much more complicated calculation. Here there's one of them where the value of m is 1, there's 6 of them where it's 2, 6 of them where it's 3, so that's the expected value. And for 4, there's 1 where it's 1, there's 14 where it's 2, there's 36 where it's 3, and there's 24 where it's 4, and again you get the average. So average expected values of parameters, or here's for alignments, how many cycles are there in a random alignment? And again, this seems like a difficult analytic problem. But a real poster child for analytic combinatorics and the idea of schemas is that we can answer these questions immediately through general transfer theorem based on the supercritical sequence schema. Let's see how that works. And this really is just a generalization of the simple proof that we did for enumeration just with the bivariate generating function, and I'll skip the details. But what we get is if we have a strongly aperiodic supercritical sequence class, then we get the expected number of G components in a random F component. We get the expectation and the standard deviation. Again, all in terms of this lambda, which is the root of G equals 1 in its radius of convergence. And again, the proof of this is just going ahead from the definitions that we've done before with bivariate generating functions and the same kind of expansion that we did for enumeration. And we could have a similar theorem for a number of components of size k and so forth to get much more detail. But again, most people are just going to look at that one thing and say, actually that first term, n over lambda g prime of lambda, that's my expected number of components. That's all I have to compute. And for example, for compositions, so my g of z is z over 1 minus z, my lambda is 1/2 as before. Lambda g prime of lambda, that's 1/2, boom. Expected number of components is n over 2. For surjections, our lambda is log 2, lambda g prime of lambda, g prime is e to the z, e to the log 2 is 2, so it's n over 2 log 2. Immediately, we get the number of components. In alignments, again, it seems like a really difficult analytic question, but it's just all about computing lambda and then multiplying that by the derivative of g evaluated at that place. In this case, it comes out to be e minus 1. Immediately, we get results like this, and we can get other kinds of results like component sizes and other things, simply by using the structure of the combinatorial class and then what we know about analysis in meromorphic asymptotics. That's one example of the power of the idea of a schema, and there are several other schemas discussed in the book.